All right, I'd like to call to order, keep this pencil in my hand, the August 2020 meeting of the Houston Astronomical Society. Welcome, everybody. Thank you very much for joining us tonight on a shaping up, I'm looking out my window, an okay night to go out and observe after this. So hopefully you'll get a chance to learn a lot here, and then afterwards go outside if you've got a telescope and take advantage of Saturn and Jupiter positioned where they are and enjoy the night sky. So my name is Joe Califf. I'm the president of the Houston Astronomical Society, and we've got a few announcements here with the club that we'd like to make before we get into our main presentation tonight. We're lucky enough to have Bill Pellerin speaking to us about the life cycle of stars. So I'd like to welcome everybody for that. So first things first, some of the club business items. There are times when we have to move the club meetings from the first Friday of the month to the second Friday of the month, and that's usually to avoid any kind of issues with holidays. And of course, in September, we have the Labor Day holiday up ahead of us. And so in times like this, we'll normally have a motion to make the change to a date. In this case, we'd like to move it to September 11th, which is the subsequent Friday, and we'll get a second. And then members of the club would vote on it. And so I'd like to see if there's a possibility that we could have interest in somebody making a motion to move the meeting to September 11th.
I make a motion to move the meeting to September 11th.
Okay, I heard Bill Spizzeri come in first. I wasn't sure who came in second.
That was Bobby.
All right, Bobby. Any seconds? So Bobby.
Second.
Second, there we go. All right, we're gonna try something a little different here. If you can look at your Zoom screen, if you're a member, go ahead and vote in this particular case to move the meeting, either in favor or oppose it. And we'll give everybody about 20 seconds to vote here.
Boy, this is like a meeting of the future.
It is, isn't it?
I don't like that.
It's like Star Trek.
Now, if we were in Star Trek, that would be good.
Yeah,
we could have a virtual meeting, right?
We would have a real virtual meeting.
On the holodeck.
Exactly.
All right, we'll give everybody about another 5 to 10 seconds to vote. If you haven't voted yet, please do so if you're a member of the HAS. And I will be ending the poll now. So looks like the motion to move the meeting in September from September 4th to September 11th has passed at 97% to 3%. So the motion passes as presented. Thank you very much, everybody, for taking the time to vote in that. And we'll move on to the next set of items. And I should have shared that screen before. I've got 3 screens open and it's a little confusing right now. All right, the other thing I wanted to mention is we started with new member orientation over the last couple of weeks. This is something that we felt was desperately needed for all the new members that we've had joining us. And the feedback that we've gotten from the people who've gone through it has been really good, really positive. So the idea with the new member orientation is that we'll take you through some of the programs that we have with the club, some of the benefits that you get with membership, take you through a little bit of what you can expect at the dark site and how to gain access to it, and answer any questions that you may have. So we think it's a great program. We're always looking to modify it and improve it as well. But if you haven't seen the emails to go out for that and you're interested in joining us at one of these meetings, our next session is going to be on Monday, August 10th. And Steve and I apologize for stepping all over the VSIG meeting that's coming up there. But if you want to join the VSIG meeting and do the new member orientation, we also have a second session on Thursday, August 13th. If you're interested in joining any of these and you don't have the details, email membership@astronomyhouston.org to get more information, and we'll pass that along to you. And I went too far. We also had some additional announcements. Stephen, I think you said you had a VSIG announcement.
Yeah, I just wanted to make my usual announcement about the VSIG. That's for those of you who don't know, that is the Visual Observing Special Interest Group here in HAS. We meet the Monday after the general meeting via Zoom, and Zoom's working really well for the VSIG, so we're going to be on Zoom permanently, even when we come back, even if in the regular meetings are back in person. And what we do, we just get together and chat about what we've been observing. If you're a new member, you can show up and just if you want to just listen to what we're talking about, you want to ask questions, we're more than happy to help. Really, anything goes. It's just a free-form discussion. The only caveat is that we're all about visual observing. So we're not going to talk about astrophotography. We're not going to get real gear-heady about our equipment, except when we're talking about things that will actually assist in our visual observing. But it'd be primarily just an observing-based discussion. And yeah, like Joe said, this month, we do have it kind of double booked with that new member orientation, but the BSIG meeting doesn't start till 7:30. So I don't know how long Joe's meeting is going to last, but
With all the questions, they're about an hour and a half.
Hour and a half. Okay. Well,
Yeah.
We'll probably still be going when that's over. So
Yeah.
just pop on over and catch us at the end. It should be fine. And the only other thing I wanted to mention is, for those of you who haven't heard, I did have one of my novice labs scheduled for tomorrow night that has been canceled, just because I've still not quite figured out the best way to go about retooling that event for the age of COVID-19. I'm hoping to get that figured out so we can actually do one next month. But I went ahead and canceled tomorrow's. So apologies for those of you who were looking forward to that. That's all I got, Joe.
I appreciate that, Stephen. Thank you very much. People who may have questions for you, what's the best way for them to get a hold of you, Stephen?
Yeah, any questions for me about the Novice Labs or about BSIG, just send me an email at stephenj@astronomyhouston.org.
Appreciate that. Thanks, Stephen. Debbie Moran had an announcement for her novice meetings. She couldn't make it tonight because she's celebrating her parents' 65th anniversary. So I think that's a good enough excuse to miss out on this particular meeting. But she did want me to tell you that we've got the next few months meetings lined up. I'm going to be presenting in September and giving everybody in our novice presentation a walkthrough of the dark side. So what we want to do is try to demystify the dark side a bit, get people familiar with all the facilities and rules and regulations that we have there. It's not a replacement for the on-site training and passing that quiz that's required in order to get the gate codes and whatnot, but really give a chance for people to kind of see what's out there before actually making the trek and ask any questions that they have. So that's in September. And then Bill Spazzeri, I believe you're presenting in October. Is that correct? Bill's on mute right now.
You are correct. How did you know that?
I
Yes,
saw the emails come across. So I don't know what the topic is. She didn't share that with me. But,
in October, I'll be presenting about the Greenwich Observatory in England, along with Stonehenge, which is right down the street and has astronomical significance.
yeah, it's actually what we patterned our dark site pads after, right? No, not really, but we call it Padhenge affectionately, right?
Okay.
All right, thank you, appreciate that. Up next, Doug McCormick. Doug, I see you're on. I think we have a whole slew of awards to hand out tonight, correct?
Yeah. Hi, everybody. I'm Doug McCormick. I'm your Astronomical League coordinator and awards chair. And I guess one of the things that's happened with COVID is we've all had a little extra time to observe, and these awards are just piling up. And I finally decided that we're just going to have to present some of these awards online here, and then I'll make arrangements to get the awards to appropriate people through either the mail or in person. Anyway, for you newbies, your regular or sustaining membership in the Houston Astronomical Society gets you a membership in the Astronomical League, which is a nationwide astronomy club made up of member organizations. That so part of your dues basically goes to pay your dues. Dues in the HAS goes to pay your dues in the Astronomical League. Lots of benefits to being a member of the Astronomical League, one of which is the opportunity to complete the various observing programs that they have as part of their observing programs. And these are all done by members. Our own Bill Pellerin, who's a speaker tonight, has actually got an Astronomical League award program on observing stellar evolution, and which is actually, I think, his topic tonight as well. So, and we also, Amelia Goldberg has also done one called Universal Sampler. Universal Sampler is a good one for the beginning observer. It has a lot of good information in that as well. So without further ado, I'm going to go through these awards, and I think we have time to give them some online applause, right, Joe?
Absolutely.
All right. So there's a small group, there's a fairly large group actually of new members of HAS that are doing the Beyond Polaris observing programs together. The first one to observe all the objects in this list is Chris Morissette. And so this is Chris Morissette's certificate for the Beyond Polaris observing program, and their pin. And Chris, are you on? I looked through all the names and didn't see you. You were going to be on. Okay, well, Chris is not on, so
I'm on. I'm here.
Oh, there you are. Hey, I see your name.
I just had to figure it out. Thank you.
Okay. Well, congratulations. Let's all unmute and give Chris a sort of recognition here, or thumbs up or something.
Yeah, there you go.
Thanks, everybody. Appreciate it.
And Chris, I'll get this to you in the mail.
Perfect.
Also, our own Joe Califf has completed the Beyond Polaris observing program, and he had his award sent directly to him. So please give Joe a hand. Thumbs.
Thank you. Thank you.
Congratulations, Joe.
Thank you. One more pin to add to the collection.
There you go. Yeah, got to get some pins. All right. So next we have Jenny Stein. I saw Jenny Stein there. She's been busy. So Jenny has completed the Northern Skies Constellation Hunter program. She got certificate number 231. And so there's Jenny's certificate. And her pin for constellations. Can you see that? Yeah, there you go. Look at that.
Nice.
That's her pin. So I'll be getting that to you. Jenny, give her a hand.
That's her there.
Next, keeping with Jenny Stein, since she's been so busy, she's completed the Binocular Messier program. There's the Binocular Messier program certificate, number 1191. That's a popular program. Here's her pin. And so congratulations, Jenny, for that.
Name next to that. Okay.
And then Jenny and her husband Robert both completed the lunar program together. So there's their lunar program certificates. Robert's is certificate number 1106. Jenny's is 1105. So Robert, she beat you. And
Hater.
yeah, there you go. And there's your pins. Those will be coming. There's some nice moons there.
Oh,
Wonderful.
nice.
Yeah.
I've been really enjoying these programs a lot. It's been really fun to kind of get me to study the skies. I really.
Well, very good. Yeah, that's what it's for, to have fun. If they're not fun, don't do them, right? So congratulations again.
Congratulations.
Mr. Stephen Jones is right there on my screen.
What's up,
He's
Doug?
been busy. First off, Stephen has completed the Astronomical League's 2 in View observing program. Pretty cool program where you have two different objects in the same view. Certificate number 39. And there's his nice, that's what the pin looks like right there. You see that? Yeah.
Oh, that's a nice pen.
It should give you 2 pins, right?
It's a 2 for 1 thing. So sorry, no. Sorry, but no. And then he's also done the Caldwell program, which is, for those of you who don't know, this is a program that's 70, or it's a list of objects, another 110 objects beyond the Messier list by Patrick Caldwell Moore. And so Stephen has got the Caldwell's Award certificate, number 266. And you get a nice big pin for that one. Yeah, there it is. Somewhere.
Thank you, Doug.
Yeah. So congratulations there, Stephen. I will get yours out at the dark side.
Okay.
I'll see you out there. You going out there this week?
Not this weekend, but
All
I'm
right.
sure I'll
Well,
make it out there sometime soon.
I'll see you out there, new moon.
Yeah.
All right. Moving on. There's a guy named Doug McCormick. Oh, that's me. I did one. I got the Northern Skies Constellation Hunter Award.
Yay.
How exciting. And I got the Observer Award. Another one of those things, another list of stuff. So that's me. Hey, hooray, hooray.
Congratulations, Doug.
Yay.
All right. And now, Stephen Goldberg. He's been over there waiting patiently.
Oh, who's that?
Well, I don't know whether he's been patient or not, but he's been waiting. Stephen has done the binocular Messier program. He got certificate number 1,197. A nice little pair of Messier binoculars there.
Ah, nice.
Congratulations, Steve.
Nice.
He has done the Northern Arc Peculiar Galaxy program, and there's his certificate.
Wow.
Number 98. And it's got a V for visual, 98 visual, and a very cool pen with a galaxy on it.
Oh, nice.
Can you see that pen? That's pretty nice, huh?
Oh, yeah.
Yeah. And in honor of all that, here's the biggie for the night. Steve has completed 10 Astronomical League programs, including the 5 core ones that are required for the Master Observer and 5 more. And so he is now an Astronomical League Master Observer.
Woo-hoo-hoo.
Good, Steve.
Congratulations, Steve.
Congratulations.
He is Master Observer number 239. 239. And
Yes, very good.
of course, you get another piece of hardware for that. There it is, the Master Observer pen. So you can just throw away all the rest of them, and this one's worth 10. I'm sure you will, right? No, okay. And Steve, I will get all your stuff to you out there at the dark site. And if I had been thinking ahead, I would have showed a picture of the engraving on the plaque. We have a plaque out there at the that stays in the observatory out at the site, and it has all the Houston Astronomical Society Master Observers on it. And Steve is the newly minted last person in there, and we now have
7?
I think 9, right?
I think
should
it's
have known
me.
that too. I'll have to go out there and count them up now.
I thought Renee was number 8, but
No, I'm still waiting to turn mine in.
oh, okay.
I think
I
we're
want to be in
we're
person,
at
but this
8
is
or
pretty
9
cool.
now, I think.
Yeah.
Anyway,
Either way, impressive
congratulations
number for the
again.
club. Yeah.
I was the most recent one, and I was 7, so I know.
Okay.
Okay, so we're at 8, and Renee's on the way. So we'll be in double-digit Master Observers here anytime.
There we go. Yeah, at the rate
Okay.
Jenny's going, she might be
Uh-oh.
number 9, right?
Yeah,
she,
watch
might,
out for
she,
Jenny.
she might get it in a couple of months here. So.
So anybody listening, if you have any questions about the Astronomical League or at the award programs, you can email me at astroleague at astronomyhouston.org.
That's it.
You can also go to the website astroleague at astroleague.org. Online, it's the AL website, and all the information about the programs is there. There's also a forum that you can post to that I know at least Renee watches. I should watch. Anyway, so that's it for me. Thanks, everybody.
Thank you, Doug. I appreciate
Thank
that.
you,
And
Doug.
congratulations to all the winners. I mean, this is fantastic. I know we've been holding off on this for a while, trying to figure out when we might be able to meet in person again. But I think if we would have waited a little longer, we would have been here for 30 or 40 minutes handing out all the awards. So good thing we got this. Yeah. So appreciate that, Doug. Thank you. And as Doug mentioned, you can go to the Astronomy League's website, Astronomical League's website, and get the information there. We also talk about these programs at a high level in our new member orientation as well. So I appreciate that. And again, congratulations to everybody. All right, so that's all the club business, and I appreciate everybody waiting patiently while we went through this. But now I wanted to introduce our guest speaker for tonight. So many of you know Bill Pellerin. If you've been a member of the Houston Astronomical Society for any amount of time, you've heard Bill's name, certainly. So Bill was president of the Houston Astronomical Society in 2012 and 2013. As the author and coordinator of the Stellar Evolution Observing Program for the Astronomical League, and we mentioned earlier, he's been very active in actually observing stars over the course of his amateur astronomy career. He's awarded 80 observers with a pin and certificate for completing the program since 2013. He's the East Texas manager for the International Dark Sky Association, a member of the McDonald Observatory Board of Visitors. And Bill, that was a wonderful presentation that they had a few weeks ago. Thanks for the invite there. And also of the American Association of Variable Star Observers, so the AAVSO. He's currently active in observing RCRB type variable stars and reporting those observations to the AAVSO. So without further ado, I'd like to introduce our guest speaker tonight, Bill Pellerin. Bill, are you, can you hear me okay?
Yeah, I can hear you.
Okay.
Let's see, what do I need to do to get my screen going here? Just hit share screen?
Yeah, just hit share
That's
screen.
sufficient.
And Bill and I used to run across each other at the YMCA downtown quite a bit, but
Yeah.
COVID's changed that.
Yeah, I haven't been since February, I think.
Oh, wow. Yeah.
Yeah, it's been a good while. All right, so can you see that?
Not quite yet. Did you hit share screen?
I did. Let me go back. Let me hit share screen again.
If you hit share screen, you should see a window that pops up, and you'll hit share again on that second window that appears.
Oh, okay. I thought the one click would do it.
Unfortunately, it's the backup system, I guess.
You have to point to the screen that you want to share in that second screen.
Oh.
Or the
there.
application. Yeah.
How's that? You see it?
Not
share.
yet.
Oh, I have to hit share again.
There it goes. It looks like it's coming up now.
Yeah, I really mean it. I want to share the screen.
And Bill, before we get started here, I was going to mention to people within Zoom, we have a chat feature. If you want to ask questions throughout the chat or throughout the presentation, I should say, hit that chat button, ask your questions in the chat window, or you can hold off to the end where we'll open it up for any questions. So go ahead, Bill.
Okay, very good. Well, thank you very much, Joe and everybody. I'm very glad to be with everybody, even if it's only virtually, and certainly look forward to getting back together in person. A couple of updates on the Astronomical League Awards. I'm up to 81 now, and 79 went to Bryant Kudnick. And so Brian is the only HAS member that I'm aware of who has completed the program, the Stellar Evolution program. So I don't know if you guys became aware of that or announced it, but Brian, I know you're on. I saw your little icon come up there. So we're going to talk about stellar evolution. One thing I want to talk about real quickly is how I got to the place where I am with regard to this program. I got interested in the subject in 2008, 2009 or so, and gave a presentation at Texas Star Party in 2010 on this subject. And when I got home from Texas Star Party, I said, well, you know, that ought to be that would be a good thing for an Astronomical League program. So in 2013, I put together a program, presented it to the, went to the AL conference and presented it to the leadership team, and it was accepted as a program. And now I'm presenting it to you guys tonight. So Joe, before I get too far into this, how much time have we got here?
You've got as much time as you need. So
okay. Well, I don't want to go on past anybody's bedtime, but
we should be fine. Yeah.
All right. So before I go forward again, Joe mentioned the fact that I'm on the board of visitors for the McDonald Observatory. We just completed our summer meeting virtually online, and it was the first time they've had to do that, and that went pretty well. I had a lot of lectures about projects in the UT astronomy. You have meet and greets with UT astronomers and staff. Of course, all this works better when you're there in person. And as a member of the Board of Visitors, you support the University of Texas Astronomy program. There are other ways to support the program. You can be a friend of the McDonald Observatory and support the work of the McDonald Observatory that way as well. If you're interested in talking about joining the Board of Visitors, get in touch with me and we'll talk about it in detail, what it entails. There is a McDonald Observing event tomorrow night at 9:45 p.m. If you go to mcdonaldobservatory.org, there is a thing that says events, and if you click that, it will take you to a link where you can join that presentation. Those typically last right at an hour. I know they're going to do Jupiter, Saturn, and a few deep sky objects tomorrow night, so it should be a good one. We hope they have good weather. As I said, the program was created in 2013. It's actually a relatively easy program for small telescopes. It wasn't intended to be an observational challenge for people like some of the programs within the Astronomical League take big telescopes in dark skies to see the objects, but this one does not, except for a few objects. There are a couple of things in there that are fairly dim. And as has been mentioned before, Amelia has the Universe Sampler program. As far as I know, that's all the HAS written programs we have. Is that true? Anybody know different? No. Okay. So I want to talk to you about stellar evolution. And I want to start by saying that everything you see in the night sky is a star or is lit up by a star. So it is a star in a galaxy, which is a collection of stars and other things, or open and globular clusters, which are collections of stars, or it's lit up by a star, which means the moons, the planets, emission nebulas, reflection nebulas, planetary nebula, and dark nebula are visible because there's a set of stars behind the nebula, and the dark nebula blocks the light from those stars from getting to you. So you see the dark nebula because there are stars behind it. So tonight, what I want to do is review very briefly. Now, this could be a whole semester's worth of college level work, I think, to understand stellar evolution in any detail. But I want to review stellar evolution at a high level. Identify a few observing opportunities associated with stellar evolution, and to get you interested in the subject matter. This is a relatively new chart that I found. It didn't exist back when I first started making this program, but I just find this chart absolutely fascinating. It is a periodic table of the elements. I'm sure everybody who's even had any sort of chemistry class will recognize this. And it shows you the origin of, let me change my pointer here. The origin of the elements. And so you can see that the first category here is Big Bang fusion, and you see hydrogen and helium over here. The most of what the universe consisted of in the early universe was hydrogen and helium with very small traces of other things. You can see a little bit over here at lithium. Everything else that you see on this chart comes from a star having created that element. So it's just fascinating to look to and say, what had to happen before that element existed? For example, gold, had to have been developed by in stars. So if you're wearing any gold jewelry, just think about the fact that gold came out of stellar process. So anyway, I won't dwell on that, but it's just an interesting chart. You can find it on Google or something. Oops, I got to use the buttons. So I want to say right up front, I'm not a astrophysicist. So if anybody wants any deep astrophysics questions, I probably won't be able to help you. But the objects I'm going to talk about in this presentation are in the sky now. I limited the objects in here to ones that are in the sky now and easy to observe. The whole program has 100 objects, as most programs do, but I just have a few of the objects that you can look at. And I think one of the great things about this whole notion of stellar evolution is you could easily spend your whole observing career observing and learning about stars. The HR diagram, which some of you may have seen and some of you may have not, tells you a lot about stellar lifetimes, and it's important to understand that diagram. It's really not that difficult. It's actually a fairly simple diagram to understand, but it also allows you to see a map of how stars evolve over time, from star birth to the end of the star's life. So I'm also going to talk about high and low mass stars. Everything about what happens to a star depends on the mass of the star. And but I'm gonna simplify this and say there's high mass stars and low mass stars, and we're going to say this is the big breaking point between what happens in the life of a star between high and low mass stars. We're going to talk about object lists and reference material. There are books that you can get. One that I've had for a number of years that I still refer to, and in fact got me interested in the subject. Oop, hit the button. So there are some strange words that are used in the context of stellar evolution that are used differently in other areas of life and other areas of science. So I want to explain those a little bit so we understand what we're talking about. When we talk about stellar evolution, we're talking about the lifetime of one star, not the intergenerational evolution of stars from one generation to the next, to the next, to the next. In biology, they talk about evolution among generations, across generations of stars, and that's not what we're talking about here. We're talking about one star and what happens to it over its lifetime. They use they use the word burning to talk about what a star is doing. It's burning hydrogen, for example. When they say it's burning, what it's really doing is nuclear fusion. The nuclear fusion is producing the energy to make the star light up. And so at different times in the star's life, different materials fuse to higher elements. And when they say burning, they mean that's the thing that's actually fusing at the moment. The next one is luminosity. Luminosity indicates the intrinsic brightness of a star, the power. So if every star were the same distance, then the only thing that would affect from us, the only thing that would affect how bright you see it is the luminosity. Now, strictly speaking, luminosity is the power that the star gives out, the integrated power. But you can think of it as brightness, assuming all stars were equidistant away. All right, the main sequence is on the HR diagram. We'll talk about that some more in a few minutes. And it's when a star is in midlife, like the sun is a midlife star, it's on the main sequence. So if somebody says a star is on the main sequence, it's a midlife star, right? It has formed, it is lit up, it is generally burning hydrogen to helium, and it's gonna, in fact, 90% of the time a star is a star, it's on the main sequence. The ash is the leftover material from nuclear fusion in stars. Hydrogen fuses to make helium. Helium is then the ash of the burning of hydrogen. Planetary nebulas are remnants of low-mass stars. Talk about that in more detail. Solar masses, we talk about stars as being measured in solar masses, which is an odd thing, I get in some ways. You know, it's very colloquial in that we say, well, our star is the one that we're going to compare all the other stars we see to. So our sun is by definition a one solar mass star. And of course, bigger stars and more massive stars are multiple solar masses. So we'll talk about that as well. When they talk about metals, when they talk about what are the contents of stars, when they do spectroscopy, what are the metals in the stars, they're talking about elements that are heavier than helium. Anything heavier than helium is a metal. So this doesn't have, the word metal in this context does not have the same notion as you and I think of it as steel or aluminum or something like that. That's not what it is. Okay, I want to talk about the HR diagram. So in 1911, two people, Elnar Hertzsprung and Henry Norris Russell, actually came up with this diagram at the same time, unbeknownst to each other. What the plot is a plot of luminosity, in other words, absolute brightness, versus temperature, which is the color of the stars, color of the star. So that's it. That's the only thing. It's two axes, and it's brightness and intrinsic brightness and temperature, color. So luminosity is on the y-axis. It increases up. So stars up here are more luminous than stars down here. Get some noise here. Why is that? Can you hear me okay?
Yeah, we can hear you. It's a little bit of static that just popped up. Let me try something.
Static over you.
Okay, it went away.
Yeah.
You got me, okay. And temperature is on the x-axis, and oddly enough, temperature increases to the left. So temperature temperatures are higher. Yeah, temperatures are higher over here than they are over here, okay? Now, when they talk about classifications of stars, here's an interesting little tidbit. They talk about stars in terms of their color. And the color in order from blue to red is OBAFGKM. OBAFGKM. The mnemonic for this has been "Oh, be a fine girl, kiss me. Oh, be a fine guy, kiss me." And that's hottest to coldest. Now, you might say, why is that? Why is that so? Well, back in the early days when a woman named Annie Jump Cannon was working at the Harvard, where they had a bunch of women doing data reduction, she was measuring spectrographs of various stars and was measuring the strength of the hydrogen line in the spectrograph. And so she put them in order based on the width of the hydrogen line. So an A star has the widest hydrogen line, the B has an X, and the C has an X, and so forth, and so on. Now it turns out that that means that when you reorganize them by color, the hydrogen line doesn't follow that. And so what you see is that an O star, which is a bright blue star, has a relatively weak hydrogen line, and an M star does too. And it turns out that, in fact, a dim star has a dim is the wrong word. An A star has a wide hydrogen line, and O star and an M star have a narrow hydrogen line. So if the star's too cool, the hydrogen line is narrow. If the star is real hot, the hydrogen line is narrow, interestingly enough. So here is a sort of a better look at the HR diagram. This line here is the main sequence. So every star that is in midlife, including the sun, which is right here, is on the main sequence. Every other star that is off the main sequence, that is, say it might be joining the main sequence out of dust and gas, is still off the main sequence but joining. Every star that has evolves off the main sequence at some point to a giant or a supergiant. Okay, and again, the temperature is much higher here at the blue stars than it is over here with the red stars. There are two very easy equations in this whole presentation, and these are them. The wavelength of light is inversely proportional to the temperature, and which means lambda equals b over t, and b is a constant. What that means is that for the sake of understanding stars, the frequency or the wavelength at which the light is most prominent is the color of the star, and then that's how they determine the color. You can do this yourself, actually, which is two filters. You can get the color of stars. But simply stated, it means blue stars are hotter than red stars. Color of stars is based on wavelength of maximum brightness. That's what I just said. And the luminosity is proportional to the temperature raised to the 4th power. So L is proportional to T to the 4th. Okay. All right. So one thing I endeavored to do for the program was to find midlife stars, in other words, stars on the main sequence that have the various colors that we talked about, and going from blue to red. And you can see this list if Joe wants. I can send him this presentation and he can put it up on the website or something. But the O star, Zeta Ophiuchi, is a very blue star Albireo with a K red companion. So I didn't list it again down here. The K star is Pollux. A star is Rosselhog in Ophiuchus. F is Theta Butis, and G is the sun. G is the sun is a G yellow star. K is an orange star. Pollux is an example of that one, and M is a red star. Rosselgatti in Hercules. So you can actually see fairly easily a set of midlife stars that cover the whole range from O to M in color. And that's one of the things why this is, as a very visual program, this is really a good thing, because you actually can see the color of these stars with your eye and a relatively modest telescope. So I've said that stars work with nuclear fusion. Main sequence stars, midlife stars, are fusing hydrogen to helium, and matter is converted to energy based on the E equals mc squared, which is maybe the most famous equation in physics. What happens when hydrogen fuses to helium? Some of the mass of the hydrogen is lost, so you don't end up with as much mass in the hydrogen that in the helium that you started with the hydrogen. And that mass that's lost is converted to energy by the equation E equals mc squared. That's how stars work. Now, so where is this happening in the star, and how does the energy get to the outside? So for very low mass stars, less than 0.8 of solar mass, the hydrogen core, which is doing where the fusion is going on, is in the center of this star. And here to these, I'll call it the surface, the thing you see of the star, is the photosphere, is the convection zone. So the material basically, or the energy, bubbles up. It's sort of like a pot of water on the stove that's boiling, and the energy from the burner is heating the water on the bottom very hot, and it's flowing to the top. This is different for a low mass star like the sun, which actually has two zones. It still has a hydrogen core, hydrogen to heliums going on. They have a radiative zone in which energy is radiated to a point, and then there's a convection zone all the way out to the outside. If you've looked at the sun with a hydrogen alpha telescope, you may see these granules in it, and that sort of looks like the top of a pot of boiling water, and that's the reason why you're seeing the convection pushing up and going back down. So it pushes up, it cools, it comes back down, it goes over and over. A high mass star does something completely different. Hydrogen core, we're assuming where it's an early high mass star. The convection zone is near the star, and the radiative zone is from there out. Now, all of this has to do with the fact that a high mass star is a much higher temperature star than a low mass star. So for the sake of this discussion, we're going to say that low mass stars are stars that are less than 8 solar masses. And the line is not hard and fast. You can't say this star is definitely 8.02 masses and it's going to do something different. But you can say as a generalization that low mass stars are going to end life as a white dwarf and planetary nebula. High mass stars, on the other hand, greater than or equal to 8 solar masses, are going to end life as a supernova with a neutron star or a black hole in the center. So a very different evolution sequence for low and high mass stars. So let's take these separately. Low mass stars, condensation of hydrogen and helium from the creation of the universe. So we all know that the universe is not a uniform distribution of material. You can look at the Planck survey and look at the cosmic background radiation, which people who know about this stuff say helps us understand why the universe is not homogenized. So you've got this mass of hydrogen and helium, and it clumps together. Gravity just takes over, and what happens is the gas condenses, and when it gets enough material and heats up sufficiently, hydrogen fusion begins. So you have a star at that moment. They call that star a ZAMS, a zero-age main sequence star, and the star joins the main sequence. Now, all of this happens in all of the nurseries that you see. You'll end up with some high mass stars just because there's more material to form the star, and you'll end up with some low mass stars in places where there is less material. The Eagle Nebula, the Swan Nebula are two examples of star forming regions. Of course, one of the more famous ones is the Orion Nebula, but that's not up now. That's a winter thing. Here's a picture of the Eagle Nebula, and there's this little part down here that they call the what do they call it? Something of pillars of creation. That's what it's called, or right here maybe. And so what's going on in there is star formation, and you can see back behind here some stars that have already lit up, but were formed by the cloud. M17, this must just be a part of it because you don't see the swan shape, but it's a star forming region. Okay, so once the star is on the main sequence fusing hydrogen to helium, it remains on the main sequence until most of the hydrogen is burned up. As I said earlier, about 90% of the lifetime star is on the main sequence. Here is that same HR diagram that I was showing you, and it shows evolutionary tracks off the main sequence. Now, one thing I want to make really clear is none of this represents actual motion of the star. It just represents that it goes to a different characteristic that we can map on the HR diagram. So you see the sun here is a hydrogen to helium, and it's on the main sequence. Okay, we'll talk about the phases that it goes through to get to where it's going to end up. So hydrogen, after hydrogen is essentially exhausted or close to it, hydrogen core burning ends and the star leaves the main sequence. Let's go back to this thing. It leaves the main sequence, and it's it's RGB, red giant star branch moving up here, up this way, and as the star gets bigger. So it leaves the main sequence. You've got a helium core ash with hydrogen shell burning. So there is enough hydrogen around the core to still burn, and inside that there's enough helium that the helium starts burning. And in fact, you can see on this diagram here, there's a thing called the helium flash right here, where helium takes over the process of burning and is the primary engine that drives the star. And this is called the horizontal branch. So it's helium to carbon and oxygen is what's going on here. All right, let's see, where are we? The luminosity increases and the star expands. It becomes a red giant on the red giant branch of the HR diagram. A star that meets this criteria is Arcturus. Arcturus, everybody can find that one easily, I think. There it is, Arcturus, a map. I actually saw Debbie's presentation last night, and she showed you how to find things, and what I hope to do tonight is actually show you what those things are and tell you something about what you're actually looking at. So here's the red giant star that started life as a low mass star. It's got a helium core that's initially inactive, hydrogen shell burning, convection zone. It's turning into a red dwarf, a red giant. The helium core turns on and helium burning at 10 to the 11th degrees Kelvin begins. The hydrogen shell continues to burn. Helium flash for low mass stars. Helium is fusion to carbon and fusing to carbon and oxygen. There is a small decrease in luminosity as the star moves back left on the horizontal branch, and you can see that. So you can see this is going down slightly. So the luminosity is going down and it's changing color a little bit. Moves to the left of the HR diagram, more blue. It spends about 2 billion years here. Observing lists for that RR Lyra as a period. It's a variable. Anything that starts with R or T or ST on through Z is a variable star. And so the period on this one's 0.567 days, magnitude 7 to 8. So you might be able to see the whole change of that star in one night of observing. That's where it is. Okay. let's see. So the hydrogen branch star structure, we said that helium core is burning, the hydrogen shell is burning, we still have convection, and it's headed this way. The star enters its second red giant phase with more luminosity than the original giant. So what's going on here is called the asymptotic giant branch. It's asymptotic because it's very close to this horizontal branch for a long time, and it gets up to here as another red giant. During this time, it has a double shell burning and a process called dredge up, which carries carbon from the core to the surface of the star, and you have carbon stars. There's a observing program called around carbon stars. So if you want to see those kind of stars, check out that program. You will also see stars that are variable at this time too. I've got another picture that shows you where the variability strip is. But a lot of times when these stars are becoming sort of late life stars, they'll go through a phase where they become variable stars. And of course, the AAVSO is very big on that. Observing list are Hercules. It has a range of 8 to 18 magnitude. So some of these ranges can be quite significant. This one says 13.5. Well, one of them's wrong. Asymptotic giant branch star. You've got, let's see what we got. Carbon and oxygen are not burning, and they won't burn. The helium shell is burning. Hydrogen shell is burning. The convection zone here is getting the heat out to the exterior of the star. The number of AGB stars is actually fairly low at any point in time. At any time in the region of space, there will be one AGB star for every 15 million main sequence stars and 3 million white dwarf stars. So when it gets to the end of being an AGB star, let me go back to the diagram here. According to this diagram, it just sort of stops, but that's not really what happens. What really happens is fusion stops. We're left with a white dwarf in the middle, emitting mostly ultraviolet light, which is leftover heat from its previous life as an actual star. It's actually something of a misnomer to call a white dwarf a star because there's no fusion going on in a white dwarf. White dwarf is just lighting up because of residual heat. So a white dwarf is dim. If you look at planetary nebula and want to look at the central star, you find that can be difficult. There are a few that are, at least one or two that are Mag 9 or so. The rest of them are Mag 10 or dimmer. The star, what it does is it's turning into a white dwarf. The material that was on the outside of the star gets shoved out. That is the material that will light up when the white dwarf is the only thing left to power this star. So the white dwarf emits a lot of UV. That UV lights up the planetary nebula, and you get to see that. Now, look fast because planetary nebula only last about 50,000 years. So you don't have forever to look at those. So observing lists, the dumbbell, you're familiar with that, the ring, nebula, M57. The white dwarf finally cools off, never to be seen again. It becomes a black dwarf. And in fact, I'll show you where it goes. Where it goes is over here, circles back around, ends up right here in this category where it says, you might not be able to read that, but it says white dwarfs. And that's the end of it. At the end of things, it becomes a black dwarf. That's the end of it. There's the dumbbell, which you've seen, I'm sure, many, many times, and the ring. Some white dwarfs can actually become a 1A supernova. I'm not going to dwell on this very much because I don't want to take the time to, but if a white dwarf is in the region where it's near a very large star and can accrete material from that star, it actually can take over some of that material and can burn that material, resulting in a recurrent, or maybe not recurrent, nova. The amount of material it accretes cannot raise the mass of the white dwarf to over 1.4 solar masses. That's the Chandrasekhar limit. And then it explodes as a 1A supernova. The important things about 1A supernovae is that they are standard candles. Since we know how much mass they had when they exploded, 1.4 solar masses, we know how much energy they're going to give up, so we know how bright they're going to be. So astronomers use those. If they see a 1A supernova, they know the intrinsic brightness. They just have to use the inverse square law to get the distance to that star. Easy, right? Okay, the high mass stars are the live fast, die young stars. Their lifetime on the main sequence is about around 20 million years compared to a low mass star like the sun, which is going to be about 10 billion years. So they're very short-lived by comparison to low mass stars. The red giant branch is similar to a low mass star's helium core surrounded by hydrogen burning shell with some changes. Helium burns to, once it gets to helium, it burns to carbon and oxygen during the red giant phase. The high mass stars has enough heat to make helium burn to carbon and oxygen. And in addition to that, it's hydrogen to helium early on, followed by helium burning, then carbon and oxygen. Star becomes a red giant, and we get to what they call a stellar onion. The observing list is Antares, which is a red giant, or Rigel. Rigel's not visible right now. But you end up with all these different shells of elements, as most stars do. It started with hydrogen, went to helium, the hydrogen shell, went to helium, carbon, oxygen, neon, magnesium, silicon, and then iron. Iron cannot be fused and create energy. So that's the end of what can happen inside a high mass star. Once it gets iron in its core, something big has to happen. The iron core cannot be fused to heavier elements. Even heavier elements are created in a process called neutron capture, which is an event that happens during a nova, a supernova. So gravity wins and the star implodes. In 1 second, the stellar core disintegrates, the collapse is followed by a rebound, and you have a supernova. And the elements that are higher in the periodic table come from that process, many of those. It is so bright that for a long time, astronomers seeing these spiral nebula believed that these spirals had to be in the Milky Way, because when they'd see a supernova, they said nothing could create as much energy as a supernova in a distant galaxy. It could not be that far away. And of course, time has shown that they are far away and they're extremely energetic. So we know better nowadays. The energy equivalent of all the energy from a sun in a lifetime, 10 to the billion years times 100, that's the amount of energy you get in a supernova. These are type 2 supernovae, okay? Observing this, the Crab Nebula, which is a winter object, that is a supernova remnant. And another very popular supernova remnant that Debbie talked about yesterday is the Veil Nebula, which she rightly said you can only see part of because it has grown so big over the many, many years since the star that created that that set of stuff has gone away. There's a picture of the veil. We saw that before. One quick discussion of variable stars. There is a thing on the HR diagram, I'll show you that in a minute, called the instability strip. There are also eclipsing variables like Algol and Beta Lyra. These are stars in which one star goes in front of another and causes it to dim. Those don't count. Those are not what we're talking about here. We're talking about intrinsic variables, Cepheid variables, RR Lyra variables, Myra variables. There's a lot of categories of variable stars. Again, looking at the HR diagram, here is a picture of one of the instability strips in the HR diagram. So a star that is in a state which is between these two lines of the instability strip can become a variable star. It's just another path on its way to the end. As I said, eclipsing are not intrinsically variable. Cepheids, high mass, variable over a few days, have a well-known period luminosity relationship discovered by Henrietta Swan Leavitt at Harvard in the early 1900s. This is the kind of star that Edwin Hubble used this information to prove that the Andromeda Galaxy was outside of the Milky Way. Prior to that, prior to his discovery in around 1930, astronomers weren't sure whether these spiral things they saw were other galaxies or, say, solar systems that were forming inside our galaxy. So what he showed is that clearly, and this is based on the Cepheid variable period luminosity relationship, that was outside the Milky Way. There's a couple of stars to look at. On RR Lyras are variable stars on the horizontal branch, usually class A, sometimes F, about a half a solar mass, so they're dim. They're old metal poor stars, often associated with globular clusters, very short periods, less than 1 day, lower end of instability strip, variable during time in horizontal branch. RR Lyra is an example of that. Myra variables, red giants, temperature less than 3,800 K, long period, 800 to 1,000 days, high luminosity, less than 2 solar masses, large amplitude, 2.5 to 11 mag, at the tip of AGB, about to become planetary nebulas. Observing list, Myra, Cetus, it's not up during TSP, not up now. Well, it might be up now. No, it's not up now, not up now, never mind. Observing this is Arachile, 5 to 12 magnitude, and Her, which should be visible now. Okay, so I want to end by showing you a couple of things. This is the book that I have really learned as much as I know about this, and I could read this. I've read it several times, and I could read it several more times before I exhaust the information in here. It's still available, although it was written in 2002 or 2003. So it's not a brand new book, but it, you know, I think the information is, you know, at a high level, it's pretty much the same. If you want to, you can go to the Astronomical League, the observing programs. If you go to the Stellar Evolution program, there is a 27-page manual that you can download and print or not print. It's a PDF, and you can read that. That contains a lot of what I talked about tonight. The Observer's Guide to Stellar Evolution, we already talked about that. Astronomy Today is a textbook. So any good college level textbook is going to have the story of stellar evolution in it. American Association of Variable Star Observers, if you get interested in variable stars. The Brightest Stars by Fred Schaff is a good book. The 100 Greatest Stars by James B. Kaler is a good book. And that's the end. Whew. We made it.
Thank you very much, Bill. That's a wonderful presentation. And
Thank you.
I found myself over the last several years being really fascinated by the entire life cycle of stars. It's, you know, like you mentioned earlier, you look up and, you know, for a long time as amateur astronomers, we want to see, you know, the globular clusters, the planetary nebula and things like that. But these stars are fascinating unto themselves. And there's just a wealth of things to observe. And the other nice thing about them is you don't necessarily need moonless nights.
No, you
They're
don't.
really dim, right?
No, you don't. So it's one thing. I think the first object I ever saw through a telescope was the Ring Nebula, but I didn't have any idea what it was or why it was interesting. So the point of studying stellar evolution is that you learn why these things are interesting and where they fit in the evolution of stars and of the universe.
Absolutely. All right, we did have one question in the chat. Let me get to that. Bear with me a second. Mitchell Ayer asked, how big are supergiants and why are they so big?
Why are they so big? Well, so if you're talking about stars that are off the main sequence, those are big because they're swelling up. They've reached a point in their life, stellar lifetime, in which the star has exhausted some of the material that it can burn, and it's become cooler. So when it becomes cooler, the size of the star gets bigger, and it becomes a supergiant. If you're talking about main sequence stars, it's simply because they started out with more mass to begin with, and more material dropped in to create the star.
Excellent. For anybody else who has questions for Bill, please feel free to unmute yourself at this point and go ahead and ask. You have a time for a few questions, right, Bill?
I have a question. This is Chris.
Hi, Chris.
Hi. Hey, you had a slide up there that talked about the low mass stars where the radiant section was near the core and the convective section was out closer to the edge. And then the high mass stars, that was reversed. And why is that? Why is the convective section for a high mass star near the core and the radiant section farther out?
Well, the answer is because a bigger star is a hotter star. And don't ask me the physics of it because I can't tell you, but I know generally speaking, the answer is the bigger star is the hotter star because it's hotter. These things switch places. The physics of it is probably beyond me, but that's what I know about it.
Okay, thank you.
Great question, Chris. Any other questions out there? Again, you'll probably have to unmute yourself to ask those questions. And while this was going on, we had a pretty lively discussion in the chat. So Justin was sharing a lot of what he knows about stellar evolution as well. So good stuff. While we're waiting for any additional questions to come in, let me go ahead and share my screen here and show you the Astronomical League website. Let me know if you can see the AL website on the screen. You see it okay? I see Bill, okay, nodding his head. I'm at astroleague.org. If you're at this page here, up at the top, you'll see this menu bar. Go to Observe. You don't have to click on any of the submenu items. Just click on Observe. And then you'll notice this link here for observing programs listed alphabetically. We scroll down here to near the bottom. There's the Stellar Evolution Observing Program. So if we click on this, you'll notice that the chairperson or the coordinator, I think they're called coordinators, correct, Bill? I know you're on mute right now, but Bill is the coordinator for this program. And if you scroll through here, you'll see a list of the requirements here on the right-hand side, all of the rules, everything else going along with it. And that PDF that Bill was referring to is down here at the bottom. So there are two PDFs here, the manual and the object list itself. So if you're interested in this, and once I finish the two that I'm working on currently, Bill, I'll get started on this one. This is a pretty interesting thing as well. So this is where you can get more information about that.
Joe, could you scroll to, oh, I'm sorry. Could
No,
you
that's
go
fine.
back to that screen and go to that same screen you were just on?
Sure. You
Can
see
you
it?
scroll to the top of that screen, please? So this is an Astronomical League Stellar Evolution program, and it has a picture of Stonehenge on it. Do we know why the Stonehenge is associated with stellar evolution?
I didn't put it there. They actually changed up some of their website stuff, and they actually made it easier. One of the things they did was put these two tables in. So they quizzed everybody who had a program, you know, to fill out a table like this, which we did. So my answer is I don't know.
Okay, just curious. Thank you.
Absolutely. Any additional questions?
Yeah, I'd like to go back to the well. This is Chris again. Bill, could you talk to me about globular clusters? What the heck are they? They seem to be kind of out in their own world, floating above the top of the galaxy. The gas that, you know, presumably created these stars is blown away. What are these things?
Well, good. That's a good question. Globular clusters are actually one of the more interesting objects in the galaxy. And there was a time when people were looking at the age of globular clusters and somehow came to the conclusion that globular clusters were older than the universe, which couldn't quite be. But what they resolved that by coming to the conclusion that globular clusters are really one of the oldest collections of stars in our galaxy. They formed back in the days when the galaxy was forming, presumably, and they're in a halo, as Debbie was talking about yesterday, above the disk of the galaxy. So they're very old stars, and it's a very early in forming collection of stars. So they're probably low metallicity, I would guess. Somebody who knows better can correct me if that's wrong, because back in the early stages of the forming of the universe, the only elements available were hydrogen and helium.
And they're
Thank
still
you.
actually theorizing on how exactly these things came to be, right? I think there's still not a complete consensus on what they are and how they came. I've heard various theories about the cores of galaxies that have been consumed by our own galaxy and other things like that. But I think people are still trying to get to the bottom of that. But as Bill said, they are very old objects and generally very metal poor because of their age.
I mean, one thing you can say for certain is that there had to be a lot of material in one place to
Right.
form a globular cluster. That's a certainty.
Absolutely. Great. Other questions? All right. Well, hey, Bill, thank you very much. It's always good to hear from you. And like I said, I find this topic absolutely fascinating. So I'm glad you could share that. And I'm hoping other people can jump on board and learn more about these types of stars through the program as well. So thank you very much, Bill. All right, and that concludes our meeting. And you know, based on the results of the vote earlier today, our next meeting is going to be on September 11th at 7 p.m. So we won't have the meeting on the first Friday to avoid the Labor Day holiday, but it will be on the second Friday. And our novice meeting will be the Thursday preceding that. So on September 10th, we'll have our novice meeting. If you have any questions about anything you saw, go to our website. We've got a lot of answers there, www.astronomyhouston.org. If you're into social media, you can find us on Facebook, Twitter, and Instagram. And if you have any questions for us, you can always email us at info@astronomyhouston.org. So that's everything I had. I appreciate everybody's time here. Again, Bill, thank you very much for the presentation. We'll have this recorded and on the website by the end of the evening tonight. And we look forward to seeing you soon. Everyone have a good night.